Okay, we have been discussing scanning electron microscope. So in scanning electron microscope, we have discussed the basic structures or basic components present in scanning electron microscope. Starting with, there is an electron gun from which electron will come out, depending on whether it is thermionic gun. In that case, the gun needs to be heated by applying appropriate voltage, or the gun can be field emitted gun where high electric field is applied at the tip, again by applying voltage, and if the electric field is more than the work function of the gun, the electron will come out. And there can be multiple anode. Some anode is for carrying out this field emission, and some anodes may be for accelerating the emitted electrons. Okay, there can be well-knit electrode that we have discussed in the last class yesterday, which is an opposite bias or negative bias, so that the electrons can do a crossover, or electrons can be squeezed towards the axis. Okay, so after anode there are a series of lenses. Lenses are electromagnetic lenses. They are not optical lens, because the electron is a charged particle. And in between lenses there are aperture. The main purpose of the aperture contains a plate with a hole at the axis, so that the electrons can pass through. The electrons which are closer to axis can pass through the aperture, so that we can avoid aberration. Okay, so these things we have discussed. We have also discussed that the SEM, that is scanning electron microscope, usually is kept in high vacuum, because otherwise these electron will not be able to reach to the target. And we need a large mean free path, so that the emitted electron will reach to the target. If there is air inside, then the electron will be absorbed by the air molecule. Okay, right? So this part we have discussed. We have also discussed a bit of interaction between the electrons and the sample. Okay, there we mentioned like three kinds of interaction. So this is my sample. Okay, and this is the incident electron, and this incident electron can generate secondary electrons. Okay, and these secondary electrons can be captured to generate image of this surface of the sample. There can be backscattered electron. Okay, and there can be X-rays coming out from the sample. And we mentioned that these secondary electrons will be generated when these incident electron interact with electrons at the outermost shell, and they come out from the outermost shell. And these electrons are very low energy. Okay, so they will, if these electrons are generated very close to the surface of the structure, then only they will be able to come out. So these electrons are known as secondary electrons. Okay, whereas if the electrons bounce back or reflected back, then those electrons are known as backscattered electrons. Okay, on the other hand, if X-ray is generated, the way X-ray is generated, if electron at nearer to nucleus is knocked off, then electrons from outer shell might jump and generate X-ray, right? So these are the ways these signals are generated. Secondary electrons are very, very important to construct the image of the sample. As we mentioned in the last class, if there are flat surfaces and nano protrusion in your sample, then what happens when these incident electron interact with the sample? These secondary electrons might come out in large number if there is nano protrusion, whereas if it is like flat surface, very few secondary electrons will come out. So you will get a very good contrast. These portion will emit largest number of secondary electrons. So these portions will look brighter, whereas the flat portion will look little bit darker compared to these bright spots because the number of secondary electrons are less, right? And so secondary electrons detectors are very close to the surface because secondary electrons are of low energy. So the detector needs to be close to the surface, and a detector contains a very small voltage so that they can attract these secondary electrons. So we can so this if I plot number of emitted electrons versus energy of the emitted electrons, then it is experimentally it was found that the secondary electrons are they have a very small energy, okay, say around 50 eV maximum, okay, whereas the backscattered electrons are of wide backscattered electrons are of energy is distributed of backscattered electron is quite large, okay, or quite wide, and ultimately you will have like you will have incident electron energy, okay. So you see that backscattered electron or wide wide variation, okay, energy distribution is wide, whereas scattered secondary electron with small energy levels, they are of low energy, maximum say around 50 eV or so, right? And secondary electrons produced from the emission of the valence electrons, okay, of constituent atoms in the specimen. Since secondary electron is very small, those generated at deep region, okay, quickly absorbed by specimen, that we mentioned in the last class. So if we have like if it is generating deep here, then the secondary electron will be reabsorbed by the specimen itself, because the secondary electron will have like a small energy, right? Only those generated at the top surface are emitted outside the specimen. This means secondary electrons are very sensitive to the surface, right? In case of backscattered electron, we can plot BAC intensity, okay, BAC intensity versus atomic number, BAC intensity versus atomic number. Let me just say 20, 40, 60 and so on, okay. So atomic number is basically Z. So as you increase Z, your backscattered electron intensity will increase, or number of backscattered electrons are those are basically scattered backward and emitted out of the specimen. They are sometimes also known as reflected electrons, since backscattered electron possesses higher energy than the secondary electrons. Information from relatively deep region can be obtained from these. Okay, BSE is sensitive to basically the Z, sensitive to Z or atomic number of the specimen. Okay, so if I have like this is my specimen or the sample, the secondary electron, I mean the incident electrons is entering, and the backscattered electron detector is like this, and it will be like reflected back, and it will be collected by this backscattered electron detector. Okay, so the higher the value of Z, higher will be this BSE intensity. So you get brighter spots in the backscatter detector if you have like higher Z. Okay. Now another very important aspect I would like to mention is that of charging effect. Okay, charging effect. This is my sample. This is say incident electron. Okay, and you know this is backscattered electron, and this is secondary electron. Now the thing is, this incident electron, after interacting with the sample surface, they basically they lost their energy and absorbed by the specimen or absorbed by the sample. Usually this sample is grounded. Okay, so these absorbed electron will go to the ground, right? These absorbed electron will go to the ground. Now the thing is, if the specimen or the sample is insulator in nature, okay, insulator in nature, or the conductivity is extremely low, in that case what happens, this incident electron can't go to the ground, can't flow through the sample and go to the ground. Okay, they basically these incident electron, they create charging effect because they will accumulate in some places. Okay, and they will create a charging effect, they will create a local negative potential. Okay, and they will basically influence the small energy secondary electron from coming out from the sample. Okay, they will prevent. Let me repeat it once more. What is charging effect? Charging effect is incident electron will come to the sample. They ultimately lose energy and absorbed by the sample. So the sample is grounded. So they will ultimately go to the ground. Now the thing is, if the sample is insulator in nature or the conductivity is extremely low, in that case these electrons will not be able to escape to the ground. They basically create local negative potential at different parts of the samples, and they influence secondary electron. So secondary electron find it difficult to come out from the sample, and this will create the charging effect. So you will get bright and dark spots in the sample surface. Okay, so that is a problem. So then you can't study the sample surface, you can't see the sample surface. Okay, so how to avoid this charging? Okay, you can do various things. One of the important and easy thing we always do in the lab when we use SEM is by coating the sample. Okay, what is coating? By coating the sample means we use we coat using gold or platinum. Very thin layer of gold or platinum is used to coat the sample so that the sample becomes conducting and it is easier for the incident electron to escape to the ground. Okay, so we always coat the sample with a very thin layer of gold or platinum. Okay, just only few nanometers. Now, so this is one technique. There are other techniques. You can reduce accelerating voltage. You remember what is accelerating voltage? Accelerating voltage is the voltage which you use at the anode to accelerate the emitted electron. So, so if you reduce the accelerating voltage, the speed of the electron to the sample or the current due to this electron beam will be lower. Okay, so that will reduce the chances of charging effect. Okay, or that will reduce the charging effect. You can also use low vacuum, little bit lower vacuum. Okay, if you do that, then there will be, yes.
Can you repeat second point, sir?
Yeah. So let me repeat from the first point itself. So this charging effect is very detrimental. You will not be able to see your nanostructure if there is charging effect. This happens often. So one of the easiest approach is to you coat your sample or your nanostructure with some noble metal like Au, PT, etc., gold, platinum, etc., very thin layer, so that that sample becomes conducting and the electron incident on the sample will escape to the ground. Okay. The second approach you can do is reduce the accelerating voltage. You remember we use accelerating voltage at the anode so that we can accelerate the electrons which are coming out from the electron gun. So if you reduce the accelerating voltage, okay, then the charging effect obviously will be reduced. Okay, because the number of electron will come to the sample will be less, or the velocity of the electron which is incident on the sample will be less, and of course that will reduce the signal strength as well, because then number of secondary electrons emitted from the surface will be less, but we will be able to avoid this charging effect. Okay, this is a second point. What about there is another approach you can adopt, use low vacuum. Okay, if you use low vacuum, particularly near the sample surface, if you use low vacuum, then the air molecule will be ionized, and those air molecule will come in contact with the sample surface, and they basically reduce this locally grown negative potential. Okay, this locally negative potential which is developed because of charging, they will neutralize it, these positive ions, positive air ions, okay, positive gas molecules, because residual gas molecules will be ionized. When it comes in contact with electron beam, they will be ionized, right? These ions, so when they come to the closure of the specimen, they reduce this negative localized charge and give better image. Right, so these are different techniques you can adopt. In the lab, we basically use this particular technique. Okay, coating the sample with with gold. Okay, gold or platinum. So we're almost done. Just only the last part I would like to mention is the about the detector. The detector is particularly secondary detectors. The secondary detectors, as I said, they are very close to that of the sample. Okay, they are very close to the sample, so that they can collect the secondary electrons. Okay, there is a collector in the secondary detector. So this is I am talking about secondary electron detector. Okay, secondary electron detector very close to that of the sample. It contains a collector. Okay, collector is basically voltage between -50 to say 250 to 300 volt. Okay, -50 volt to say 250 to 300 volt. Okay, and so this small voltage will be good enough to collect secondary electrons. Okay, so this collector they will collect or attract the secondary electrons. You can vary this voltage so that you can control the amount of secondary electron coming out from the sample. Okay, if this voltage is too much, if this voltage is too much, then it will attract the backscattered electron also. So that's not the purpose. The purpose is to attract the secondary electron which is low in energy. So you give like few hundreds of volt. Okay, and so sometime you can give negative voltage also to repel the secondary electrons and so on. And so after this collector there is a scintillator. Sorry. After this collector there is a scintillator. So this is scintillator. Scintillator contains much higher voltage, plus 10 kV. Okay, of the order of plus 10 kV. So this secondary electron will incident on this scintillator. So once this secondary electron enters the collector, they will be accelerated and they bombard on this scintillator. Okay, by this high accelerating voltage 10 kV. Okay, so this will then emit light. These will then emit light. These electrons will then emit light. There will be light guard and photomultiplier. So there will be photomultiplier. This photomultiplier basically helps in multiply the signal, and ultimately it will generate electron here and amplify it. Okay, so that it can ultimately give you images. Images can be in the form of in cathode ray tube or I mean display nowadays, LCD based display and so on. So this is in a nutshell how this secondary electron detector is. There is a collector which contains a small amount of voltage just to collect those secondary electrons. Then there is a unit which the first part of it is a scintillator which contains much higher voltage so that it can be accelerated those secondary electrons which is come inside the collector, and these when they incident on the scintillator they will emit light or generate light. This light will be guided and multiplied by the photomultiplier. Ultimately that again generate electrons, and those electrons will be amplified, and ultimately they will form image of in cathode ray tube or LCD display. Okay, so this is how you generate the image of your surface. As I said, that secondary electron is very sensitive to the surface. If it is very close to the surface, then only the secondary electron will be come out, and there is if there is nano protrusion, more number of secondary electrons is come out. If there is flat surface, then less number of secondary electrons will come out, and clearly there will be distinction or contrast whether there is nano protrusion or whether there is flat surface, and you can then recreate the image of the surface. Okay, so this is extremely handy equipment, and this is as good as like optical microscope. Okay, but you can have images of the order of few nanometer, as I said already. So this is all I would like to talk about ACM. Okay, as I mentioned, there are two kinds of guns. Okay, one is like thermally generated thermal electron gun, and other one is field emitted gun. Okay, so thermally emitted gun and field emitted gun, so they have their own advantages and disadvantages. And energy spread So the energy spread of the order of EV in case of thermally generated gun is like 3 to 4 electron volt. Okay, whereas this is say of at least one order magnitude less, 0.3 ev electron volt. Okay, lifetime maybe few tens of hours. Okay, maybe few tens of hours to few hundred hours, say 50 hours to 500 hours, whereas this one has say very good lifetime, several years. Okay, this is, I mentioned you already that the field emitted gun has much higher lifetime, okay, compared to that of the thermionic emitted gun. And so this the cathode temperature or the electron gun temperature is very high. Okay, say of the order of 2800 degrees centigrade, whereas here it is around 300 degrees centigrade. Okay, because I mean this gun will also heat up because you are applying very high voltage, I mean very high electric field at the tip, but you see the temperature is much less compared to that of the thermionic emitted gun. Okay, now the thing is, I told you that the entire ACM is you keep it at high vacuum. These high vacuum will not only help you to increase the lifetime of the not only help you by increasing the mean free path of the electron, it also improves the lifetime of your gun. Okay, if it is thermionic emitted gun and if there is enough oxygen molecule in the chamber, that will oxidize the gun. Okay, and that will deteriorate the lifetime of the gun. So it is important that not only for improving the mean free path you make the chamber to high vacuum, it is also important to improve I mean that will also improve the lifetime of your gun. Okay, otherwise the gun, both the thermionic emitted gun and a field emitted gun, they will be oxidized or there will be oxide coating on top of the gun, which will deteriorate their performance. So for both this reason we need the very high vacuum, okay, of the chamber. Now that's all what I have to say about ACM. Briefly, today I will cover another equipment, okay, which is known as STM. Okay, which is known as STM. STM is scanning tunneling microscope. Scanning tunneling microscope. Okay. Scanning tunneling microscope or STM. Scanning tunneling microscope or STM is also used to get surface morphology. Okay, surface morphology of your sample. Now, so it will give you height of your sample. Okay, it will give you height of your sample. It will give you also your sample size and so on and so forth. Okay, now the thing is I mean nanostructure size and so on. So this STM, the way it works is as the name suggests, in the form of tunneling. Okay, so STM contains a very sharp tip, very sharp tip. So very sharp metallic tip it contains. Okay, so the basic working principle is there is a metallic tip, very sharp metallic tip, and there is this your nanomaterial surface. So you apply a voltage. Okay, then what happens is you bring this tip very close to the sample. So if you bring this tip very close to the sample, there will be tunnel current. You remember we discussed tunneling. What is tunneling? So the electron or the atomic particle can penetrate the barrier, even its energy less than the barrier height. You remember we talked about tunneling, resonant tunnel diode and all that. So what is tunneling? Tunneling, we mentioned, like if an electron has lower energy than the potential barrier, then also there is a possibility that the electron might be able to tunnel, okay, might be able to penetrate that barrier. So this is what this can happen here as well. The electrons present in the sample, if your tip is very close to the sample, then and you are applying large electric field, then the electron will be able to tunnel this barrier, okay, or this gap, and reach the metal tip, and you can then measure the current present in the circuit, okay, and know about the surface morphology. So this is the basic idea. Now there are, so one bottleneck of this particular technique, STM technique, is your sample has to be conducting. If it is not conducting, you hardly get tunnel current, okay, you hardly get tunnel current. But this is very sensitive equipment, okay. In fact, when you use STM, in our lab we have STM, so we don't use it in the daytime, we use at night when there is no one in the department, okay. Or you have to have like your equipment you have to put in a table which is like vibration free, okay. So it is very sensitive, right? So my students use STM at night when there is hardly anyone in the department. So you need to use it in a almost vibration free environment, okay. Now what is so this is the basic working principle. Only the bottleneck is the sample has to be conducting. If the sample is insulating, it hardly works, okay, it will not work. Now so how you are going to scan, so you are basically scanning this, it's like yes, ACM. In ACM also you do like raster scan, right? You are scanning with electron beam. Either you will scan, move the electron beam, or you move the sample in ACM, okay. You can also rotate or tilt the sample in ACM, right? Here what you can do, you are scanning, say in the raster scan mode, you are scanning your sample, a very tiny place you need to scan, okay. Now the thing is, there are two modes of operation. One is constant height mode and another is constant current mode, okay. So one is constant height mode, another is constant current mode. Constant height mode and constant current mode. So what is constant height mode? Constant height mode is you have your nanostructure and you have the tip. You will not change the height of the tip. You keep the height of the tip same, okay. So what happens, say here the distance between the tip and the surface is d1, here it may be say d2, and so on. So depending on the distance between the surface and the tip, your current is going to change, right? You are not changing the height, so you are keeping the height constant, and you are scanning the tip, you are scanning the surface with the tip, okay. And if the tip is closer to the surface, the tunnel current is more. If it is away from the surface, tunnel current is less. It is very sensitive because the tunnel current is exponentially related to the this distance, okay, exponentially related to other parameters are there, exponential d, okay. So if the d is less, we will get lot of tunnel current. if the D is higher, we will get much lower turn current, but this exponential turn makes the instrument very sensitive. Okay, exponential with distance, this tunnel current. Now the thing is, this is constant height mode. What about constant current mode? In constant current mode, you see, in constant height mode, what you are ultimately getting, you are getting different currents, and from different currents you are basically replicating the surface of the nanostructure, right? Similarly, in constant current mode, what you do, you have like again this nanomaterial surface, you have this tip, and you have this current measuring equipment, and you have this voltage source and so on. So here what you do, you are again scanning with this tip, okay, but there is a feedback system. So this feedback system, what it does, okay, feedback system, what it does, as soon as there is change in the current, as soon as there is change in the current, it sends feedback, and it then increase or decrease the value of D, so that the D remains the same. Okay, if D remains the same, your current will remain the same. So that is constant current mode. So whenever you have this D, and then you go to the other place, you see your D increases. So as soon as D increases, it gets the feedback, it changes the tip, it brings closer, so that D remains the same. Again, if the surface is like this, the tip goes up to keep the D remains the same. Okay, so this change in the position of the tip will give you the information of the, so this error current I1 minus I2. Okay, so that you are basically changing through this feedback system, so that your current remain the same, and you are changing your tip, you are moving your tip, so that your current remains the same, because it is a constant current mode. Okay, so this change in tip position you can map and develop the surface morphology. Okay, so these are the two techniques through which you can basically use STM. Now this STM is, as I mentioned, the main bottleneck is you have to use a conducting material. You can't use an insulating material. So if you have a insulating if your nanostructure is a non-conducting material based, okay, then you can't use STM. Then you can use another equipment which is known as AFM. AFM is atomic force microscopy or atomic force microscope. AFM, atomic force microscope. Okay, so this atomic force microscope or AFM will be very useful. It works in the same manner, but it can accommodate even the material is insulating. Okay, but here you don't measure tunnel current, you measure the force exists between the tip and the nanostructure. You measure the force. So this is more fundamental, because you are measuring the atomic force exists between the tip, okay, tip of this probe and the nanosurface. Okay, so this atomic force microscopy we will discuss in more detail in the next class, where you will see that in the atomic force microscopy you keep the tip very close to the surface. Okay, very close to the surface, and then you basically measure the position of the tip. So here we in atomic force microscopy we basically use a cantilever. Okay, cantilever we use, and that cantilever contains a gold coating. Okay, and there is a tip at the end of the cantilever, and this cantilever you basically move very close to the surface. Okay, so that it can sense the force. What kind of force it is we will discuss in the next class. Okay, so this because of this force there is a small change in the position of the cantilever. So there is a laser, okay, there is a laser light incident on the on this gold coating, gold patch, and reflected back, and there is a array of photo detector, and from this photo detector you will be able to map the height and position of this nanostructure, okay, how this cantilever is moving. So through this cantilever you are scanning this nanostructure by measuring the atomic force exists between the tip in the nano and the nanostructure, whereas this laser light will be reflected from this gold coating portion on the cantilever and will give current to this photo detector. There is array of photo detectors and it gives current. Depending on which photo detector current will increase, we know in which position we are getting the position of the cantilever. This in turn then you can map the nanostructure. Okay, so how it works we will discuss in more detail in in coming Monday, next class. Okay, so thank you very much. Do you have any doubt? You have any doubt?
No, sir.
Okay, so these equipment was covered before in any class?
No, sir.
Okay, so here I am covering them very briefly because there are also courses in the institute which covers maybe 2-3 of such equipment for half a semester. Okay, so as this is not that kind of course, I am covering very briefly, just explaining the working principle. Okay. Okay, so thank you very much for your attention.
Excuse me, sir.
Yeah.